Hello, and welcome to our introductory session on Boolean algebra. Boolean algebra, including its many identities, theorems, and laws, allows us to manipulate and simplify logic expressions so we can put together digital logic circuits that are more efficient and less power hungry. Boolean algebra was originally invented by George Boole in 1854, long before digital circuits took over the world. At that time, Boolean algebra was applied to logic and mathematics alone, but now Boolean algebra can be used to simplify and modify logic for the purposes of building and modifying a wide range of digital logic circuits. We can prove Boolean algebra properties and come up with more properties using one of two different techniques or a combination thereof. The first uses deductive reasoning, whereby we apply existing properties to come up with new ones. The other is through perfect induction, whereby we consider all possible input combinations for a particular property and prove that the relationship works for all possible input combinations. We'll look at both types of proof today. Before we begin, though, let's take a look at what the symbols mean. We looked at before what the AND function is, and the AND function in Boolean algebra is represented simply by the multiplication sign, the dot, or in shorthand we represent it as two variables adjacent to one another with no dot. OR, on the other hand, is represented by the plus sign. XOR is represented by a plus sign with a circle around it. XNOR is simply XOR with an inversion bar over the top. NAND is expressed by the AND function with an inversion bar over the top. And one variable with a bar over it implies not or inversion. And for shorthand for the not symbol, we often use the apostrophe to mean the same thing as the over bar, depending on what's more convenient for our word processor. The truth tables help us fully describe a Boolean function. So in this example, we have three input variables, x, y, and z, and we want to compute the output function, quantity x or y, all ANDed with z naught. In order to come up with the output accurately on the first try, it's often helpful to create helper columns. So we've created two helper columns here, one of which represents the first term in our output expression, and the other of which represents our second term, or z naught. After we calculate these two helper problems, it's a simple matter of computing the AND of these two helper columns to come up with the output. So for example, in this line of the truth table, first we compute 1 or 0, which is equal to 1. Then we compute z naught, which is equal to 1. And then we OR 1 or 1 together to get 1. And this process, by adding these helper columns, just helps us be a little bit more accurate in the computation of out. Likewise, on the last line of the truth table here, first we compute x or y. 1 or 1 gives us an output of 1. Z is equal to 1, so z naught is equal to 0. And then 1 or 0 simply gives us 1 and 0 simply gives us an output of 0. Now there are many properties, rules, theorems, laws of Boolean algebra, established and new ones that we can derive by perfect induction. And the goal in perfect induction will consider the left-hand side of the equation and the right-hand side with all possible combinations of the input variables. In this example, there's only one input variable, so the two input combinations are 0 and 1. And in the first case, when x is equal to 0, 0 or 0 is equal to 0. And when we look at 1, what we see is that 1 or 0 is equal to 1. So that gives us 0 or 1 as x or 0 on the left-hand side of the equation. And on the right-hand side of the equation, we simply have x. Are these two equal? Indeed they are. So that proves by perfect induction that x or 0 is equal to x. We can do the same thing with more complicated expressions. Here, we'll look at the distributive law of Boolean algebra. Again, we'll set out to prove that the left-hand side and the right-hand side of the equation are equal. So in this left-hand truth table here, we'll compute x or y and, x and quantity y or z. We'll put x in one helper column, y or z in another. And let's take a look at an example of how this works. So in the third line of the truth table, y or z is 1 or 0, which produces a 1. X is copied here as 0, and then 0 and 1 is equal to 0. And so on down the remaining 7 lines of the truth table. In the right-hand side of the truth table, we'll look at two helper columns xy or xz, since our goal is to prove that xy or xz is equivalent to what we came up with in the left-hand truth table. And if we look at one of the lines here, let's look at the first line. X and y is 0 and 0, which gives us 0. X and z is 0 and 0, which gives us another 0. And 0 or 0 gives us an output of 0. So as we go down the line, we find that, indeed, the right-hand side of the equation is identical to the left-hand side, thus proving by perfect induction that these two expressions are equal. In another example by perfect induction, here we have again two input variables. Therefore, we have 4 input combinations for those variables. On the left-hand side of the equation, we're going to OR together x or xy to get the output. And the right-hand side of the equation, we're just going to set out equal to x. So the left-hand truth table considers here the left-hand side of the equation for out, and the rightmost truth table considers the right-hand side of the equation. And we can see here as we take x, 0, or x and y, 0, we get 0. And going down the line, we get combination 0, 1, 0, 1, which is identical to what we get on the right-hand side. And again, we have proven by perfect induction this time that x or x and y is equal to x. Now we can also combine deductive reasoning with perfect induction to prove the same Boolean law. And deductive reasoning just means that we apply existing relationships we know to be true to derive a new relationship. So let's see how this works. Well, in the first case here, we've simplified out by using the distributive law to pull x out of the equation and put 1 or y by itself in parentheses. Now we'd like to take a look at 1 or y. What does that equal to? Well, if we look down here at our truth tables again, we can see that x and 1 or y is indeed equal to x. In the rightmost truth table here, we've just copied x. And in the leftmost truth table, we've actually computed x and 1 or y. So we've effectively taken the and of the first column in the truth table and the third column and come up with 0, 1, 0, 1, which is identical to the truth table on the right. And therefore, by perfect induction, we've proven that x and 1 or y is equal to x. And finally, we've proven that x or xy is equal to x. So this was an example of combining perfect induction and deductive reasoning. In this next example, we can prove the advanced Boolean law that x and x naught or y is simply equal to xy by again using a combination of deductive reasoning and perfect induction. We'll start here with the left-hand side of the equation, and we'll go ahead and multiply it out. X times quantity x naught or y just gives us x and x naught, or x and y. By perfect induction here, shown in the truth table on the top, we can prove that x and the complement of x is always equal to 0, which allows us to simplify this term and get 0 or xy. By perfect induction again, we can show that 0 or any variable is equal to that variable, and we show that over here in this bottom truth table. Once we've proven it using perfect induction, we can then apply it to the expression we're trying to simplify and show that indeed 0 or xy is equal to xy. So in this way, we started with the left-hand side of the equation and we ended up with the right-hand side of the equation, thus proving that this advanced Boolean law is indeed true. There are a wide variety of Boolean properties that come from perfect induction, and some from deductive reasoning, some from a combination of both. All the ones shown here are those shown for a single variable, here denoted by A. And these expressions are applied many times to simplify Boolean expressions, but we also have a variety of laws that require 2 variables to implement, or even 3 variables. These laws shown on this slide are very similar to the ones we use in regular algebra for algebraic manipulation, or moving around variables. And as you would expect, they apply with Boolean algebra as well. This next slide here looks at a variety of other laws that come in handy, and to prove any of these laws we could use perfect induction. We could use a combination of perfect induction or deductive reasoning, or we could use deductive reasoning alone. So let's take the first redundancy law as an example of how we might apply deductive reasoning to prove that this law is actually true. So what we'll do here is we'll just multiply through x and x, or y and x, or x and y naught, or y and y naught. From the previous slide, we know x and x is simply equal to x. We know that y and y naught is simply equal to 0, which gives us x, or, rearranging, xy, or xy naught. Anything ORed with itself with 0 just gives that variable, so we can simplify further as x or xy, or xy naught. And then we can go to the next step with the distributive law and pull out the x in this expression. Any variable ORed with 1 is simply equal to 1, which gives us x and 1. Any variable ANDed with 1 simply gives that variable back. And finally, we can distribute the x out again. Any variable ORed with 1 will simply give a 1, which ultimately leads us to x. So any of these laws shown on this slide we can either prove through perfect induction or through the deductive reasoning that we just illustrated with one of the redundancy laws. A last important property of Boolean algebra, particularly for digital logic circuits, is De Morgan's theorem, shown in 2 versions here. And we can prove either of these functions, either using deductive reasoning or proof by induction. In this case, in De Morgan's case, proof by induction works much better. So let's take a look what happens here with this first relationship, where again in inductive proofs we're looking to prove that the left-hand side of the equation is equal to the right-hand side of the equation. So we have 2 variables, x and y, which result in 4 input combinations. And in this first truth table, our goal will be to prove that x, y naught is going to be equal to the right-hand side of the equation. To prove that, we'll just draw up another truth table that considers x naught or y naught independently. And in this last column here, we'll produce x or naught or y naught, which is simply the right-hand side of the equation in De Morgan's theorem. And now when we go ahead and look at these expressions, x and y here in this first truth table, 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, and finally 1 and 1 is 1, and the opposite of that, simply 1, 1, 1, 0 here. On the other side, we'll need to invert x and y first before we compute the final output for the right-hand side of the equation. And then we'll OR those together to come up with the expression on the right-hand side of the equation. Finally, we can see that both truth tables produce the same output, so we've proven the first law of De Morgan's theorem by perfect induction or by inductive proof. Now we can simplify some really complex logic functions using this combination of Boolean identities and laws. As an example here, let's take a look at how we would simplify this expression. Going from the first line to the second line, we've just used the distributive law to pull A out of the equation and C out of the equation. Once we've done that, we can go ahead and notice that A or 1, any variable ORed with itself, A or 1, is going to give us 1, which we've shown here. And we apply the other property that any variable ORed with its complement will also produce a 1. And we've also applied in this line of the truth table that any variable now ANDed with 1 is that variable. So A or C and A and 1, which results here when we replace D or D naught with 1, is just going to give us that variable, in this case A or C and A. From there, we can distribute out A again and multiply out to get AA or AC or C and 1. Then we apply the fact that any variable ANDed with itself is equal to that variable, which simply gives us C in this case. And we also notice on this next line that any variable ANDed with itself is simply that variable. And finally, in this next line, we'll apply the distributive law one more time to get C times the quantity A or 1. Any variable ORed with itself simply gives 1. A or 1 is equal to 1. And any variable ANDed with 1 gives us a value of that variable. So here we've shown that this fairly complex Boolean expression simplifies down to just A or C. And throughout this all, we've used deductive reasoning here, although we could revert to proof by perfect induction if we needed to. So we can see that all the laws and theorems of Boolean algebra can certainly be used to simplify and manipulate Boolean expressions. But our goal in so doing is not simply for mathematic purposes, but to implement digital logic circuits in a more space-efficient and less power-hungry manner. Well, that's all for Boolean algebra today. Thanks for joining us as we continue to explore the world of digital logic and circuits, and we hope you'll join us again soon.